Welcome back to another video with us here at LMD and STEM Academy. In this video, we will be working through the June 2023 Physics Unit 2 Paper 2. Now, this is the first question from Module 1, so it's 1A, and it says that a mass M is projected horizontally with constant velocity umx in a gravitational field. A charge Q is projected horizontally with constant velocity uqx in a vertical electric field. Okay? The table below shows the comparisons of the physical properties and equations associated with the two cases above after a time t. Okay, so here we have our physical properties or equation being described here. And then we have two examples in each case filled out for us. We have the gravitational field case where we have the horizontal displacement and the vertical acceleration filled out. And in the electrical field case, we also have the same. We have the horizontal displacement in that electric field, and we also have the vertical acceleration in that electric field. Okay, so here's a question now. Using conventional symbols for physical quantities, complete column 2 and column 3 of the table. So we have to fill out all of these equations here as well as the trajectory. Okay, so the best way to approach this is just to draw a little sketch, right? Sketch a little, a little image of what's going on here. And so let's draw the gravitational field case. Let's start there, right? Let's start there. So for the gravitational field case, right, where we have that mass M, right, being projected horizontally, right, we can draw that as such. So here's my gravitational, so I'm just going to put gravitational field case. So that's my first case there. Right, in the gravitational field case, this is what we're working with. So here is my Y, my vertical direction, and here is my horizontal direction, right? So the mass is being projected horizontally, right? And so it's in a gravitational field. So let me just draw some field lines real quickly. So let's say the gravitational field is running in that direction, right? So then my mass M is projected that way, right? Horizontally. So that's my mass M. And that's being projected horizontally with an initial velocity of umx, right? So it's being projected into this gravitational field. And we know that when a mass is projected into a gravitational field, we know that it will experience a force that will cause it to follow a parabolic path. So I'm just going to show the path being parabolic, right? So it's a parabolic path that goes that way until it emerges from the field. So that's what we have in the gravitational field case. So I'm going to put the electric field case down here, just a rough sketch so that we have an idea as to what are the variables, what are the physical quantities that are going to be at play, right? So my electric field case now, I'm going to draw an electric field. So I'm going to draw two parallel plates here. I'm going to make my upper one my negative plate, and I'm going to make the lower one my positive plate. And so my field lines are going to run from positive to negative. So I'm going to show my field lines running upward, okay? So here are my field lines, electric field lines. So it's because that's my electric field there in the middle, in between those two plates, right? So now what do we have? We have a charge Q being projected horizontally again. So imagine it's coming in like this, right? And say it's an electron, right? That's shooting in. So it's coming in, and it's coming in with a velocity uqx. That's what they told us, right? That's what it's coming in with. And again, while the electron is in the electric field, it's going to feel a force that's going to cause it to follow a parabolic path again until when it leaves the field, it's just going to like shoot off and follow a straight line once it comes out of the field. But within the electric field and within the gravitational field, that particle is going to follow a parabolic trajectory, right? So the first thing that we can put in our table is a trajectory, right? Let's start there. So they're both going to follow a parabolic trajectory, as we said, bam, bam. And we know that from our work on projectile motion in Unit 1. So the trajectory here is going to be parabolic in both cases. So let's just fill that in and start collecting our marks. This entire table is worth 10 marks, right? So we're going to be very careful in filling it out. But the last row we already have, parabolic, okay? All right, so let's go back up here now. Vertical velocity, an equation for vertical velocity in the gravitational field case. Okay, so to come up with that, you know we're going to be needing to rely on our kinematic equation. So if I need to find my vertical velocity, which I'm going to call here as V in the y direction, right? So what we're going to do here is we're going to say, okay, I can use this kinematic equation which says V is equal to U plus AT, right? Initially, because the mass is being projected in the horizontal direction, it doesn't have a y. It doesn't have an initial y. So that's 0, okay? So the Vy is then going to be equal to the acceleration times time. And they already told us that the acceleration is g from here. So that's just going to be gt, right? And so we're going to just fill out that. So Vy is going to be equal to g times t. Okay, again, my initial velocity in the y was 0, so that went away and I remain with that. All right, let's do a similar thing for the electric field case, right? Again, we're going to use our kinematic equations. So I would say that Vy is equal to the initial y plus AT. Again, it's being projected horizontally into the field. And so the only thing that we have is that we have a velocity in the horizontal, but we don't have any in the y initially. So that goes to 0. But now the acceleration, right, is due to the force that is felt in the electric field. And they told us what that acceleration was up here. It's EQ over m. So it's just AT, but then that A is now EQ over m in this electric field case, right? So it's EQ over m times t. Okay, so that's our Vy for the electric field case. So Vy is going to be equal to EQ, right? Just your acceleration, which is given here, over m times the time. All right. So now we're moving along to vertical displacement, and we can denote vertical displacement as S in the y direction, right? They told us that horizontal is S in the X. So we're going to say, okay, in the vertical direction is SY. Okay, so we're going to use the other kinematic equation now to represent displacement. So that will be what? UT, so U in the Y times T plus a half AT squared. So that's the kinematic equation that we're going to pull for now. Again, U in the Y is 0 because initially it's only going in the X. It's being projected horizontally. So U in the Y is 0. So this whole thing goes away and we're left with SY being equal to half AT squared, right? And in the table, they already told us that the A is G is equal to G. So then SY is going to be half GT squared. So I'm just going to drop that in our table now. So SY for the gravitational field case is equal to half GT squared. Okay, so let's go to our electric field case now. So in our electric field case, again, we're going to pull for the same SY is equal to UYT plus a half AT squared. That's where we're starting from, right? Again, in the y initially, there is no velocity because it's being projected horizontally. So that goes away and we're left with Sy is equal to half AT squared, and the A in this case is EQ over M, right? EQ, so it's half EQ over M T squared, right? So that is my vertical displacement for the electric field case, right? So we can just write that there. So Sy is equal to half EQ over M, that's my acceleration, right? Half EQ over M times the T squared. All right, so that's my vertical displacement. Vertical force now. Force is a nice, straightforward one. In the gravitational case, we know that F is equal to ma, right? From Newton's laws, we know F is equal to ma. The A is the gravitational field in this case. So then your F will just be equal to mg, right? And so we're just going to drop that there. So F is equal to mass times gravity. All right, so that's a weight essentially. That's a weight there, okay? All right. So then for this, so it's F in the y direction, right? The force is being felt in this direction. And similarly for here, the force is being felt in here. But for the electric field case, right, your F is going to be equal to your electric field strength times the charge, right? And so F is equal to EQ, right? For the gravitational field case. For the electrical field case, the electric field case, right? So Fy is equal to the electric field strength times the charge of that particle that's being projected. So finally now we have the field strength, right? So for the field strength, it's a gravitational field strength that we're doing first, and that gravitational field strength is gonna be G represented by little g, and that G is equal to the force in the y over mass. And then in this case, the electric field strength is E is going to be equal to what? The force that's being felt in the y divided by the charge that's being projected. Okay? And so we're going to just drop that here. So the gravitational field strength is G is equal to F in the y over the mass of the particle that's being projected. And then here, the electric field strength is going to be equal to the force in the y direction divided by the charge that's being projected, right? And so with that, we've completed this table. We're going to be relying on it throughout the rest of the question, but it's good that we've been able to complete it. 10 marks, done. All right, so moving along now. Okay, so we're moving along now, and it says that for part B, the figure below shows the path traversed by an electron beam as it passes between charged horizontal plates V1 and V2, and how the beam is deflected on its way to form a spot on a fluorescent screen. Assume that all motions takes place in vacuum, and then V1 and V2 are separated by a distance of 12 millimeters and have a potential difference of 50 volts between them. Okay, so here we have an electron gun. Here's a cathode, here's an anode. And so the electron is being, right, launched from here into the electric field. We know it's going to follow a parabolic path inside here, and then it's going to emerge in a straight line that way, and it's going to form something on the screen, right? It's going to form an image on the screen, a spot on the screen. So we're given the width of the plates themselves, right? So it's 5 centimeters. And the distance between them, the separation is 12 millimeters. And then we know we're given that the potential difference between them is 50 volts. So in between here, right? So that volt is 50 volts. So we have a lot of information here. So let's see what is being asked of us to do from a calculation standpoint. So this is the figure that we're working with. All right, so let's go here. All right, so for B part 1, it is saying that we're supposed to determine the magnitude of the electric field between the plates. Okay, magnitude of the electric field, so that is your electric field strength that you're being asked to find. So let me just drop on here again that we said the question told us that the volt there, right, the potential difference is 50 volts. They told us that. All right, so now if it is that we need to find the electric magnitude of the electric field, that's your electric field strength E. From the earlier table, we knew that when we launched a charged particle horizontally into an electric field, we know that the electric field strength E can be represented as, what was E? E was, well, in the table, right, we said that it would have been the force per unit charge, but we're not given a force just yet. And so there's another formula that we can use based on the information that we have. And that one is that E is equal to V over D. So the D is the distance, is the separation distance, right? And that is this guy here. So that's our D. And we have our V. And so all we have to do at this point is just plug in to get our electric field strength. So that will be 50 volts divided by 12 times 10 to the minus 3 meters. When we plug that and work that through, we're going to come out with a value of 4,170 volts per meter. So that is our electric field strength, the magnitude. Okay, I just want the magnitude of it. So let me just box this. All right, that's our answer there for B part 1. Okay, so moving right along now, moving along to part 2 here. So part 2 says, hence, in light of the fact that we just got the electric field, the magnitude of it, we're supposed to now calculate the vertical acceleration of the electrons as they pass through the plate. Okay, so remember now, these are my field lines. My field lines are going in this direction because it's going from positive to negative. So those are my field lines. My electron is coming in horizontally. It comes in and then it's going to get what? Follow a parabolic path until it emerges. So let me draw that again. It's coming in, follow a parabolic path within, inside, and then it just emerges and then forms a spot on the screen. So as the electron comes in, right, we know from the question that it has an initial horizontal velocity of u, q, x, right? They told us that. Once it enters the electric field, it experiences a force, right? And that force we denoted earlier as Fy. So it experiences a force in the y direction because that's where the electric field is running. It's a vertical electric field. So the force is going to be experienced in the y direction. So we know that F is equal to mass times acceleration in that electric field, right? The acceleration is going to be due to the electric field and the force that the particles feel in there. And so if we need to find the vertical acceleration, then we can use this formula. And earlier we got that the AE, right, from the table, we knew that the AE was equal to the EQ, electric field strength times the charge over the mass, right? We knew that from earlier. So we just calculated the E. So all we have to do is just plug in the E, the electric field strength, plug in the charge of the electron, plug in the mass of the electron. So that's the mass of the electron that's being projected in, right? So AE then is going to be equal to 4,170. That's what we had gotten, right? Times the charge of an electron, which is 1.6 times 10 to the negative 19 divided by the mass of an electron now, which is 9.11 times 10 to the negative 31. All right, my units, everything is in SI unit because this is in volts per meter, this is in coulombs, and this is in kilograms. So my AE should work out to have units of acceleration, SI units. And so when I plug in everything in my calculator here, I'm coming up with a value of 7.32 times 10 to the 14 meters per second squared, because it's acceleration, right? So let me box that. This is our answer that we are submitting for the acceleration. Vertical acceleration, right? Why is it vertical? Because the force is felt vertically because the electric field is running vertically. Okay? So that's what we have here, and that is our vertical acceleration of the electrons as they pass through the electric field. All right. So we have that now. So let's move ahead. So we're at question C now, part C. So the table below shows the negative vertical displacement of electrons SY at various times during their flight between the plates V1 and V2. All right. So let's just go back here real quick and look at this image again, right? So in this image, we see that, so we're starting here. The electrons are projecting in here, right? With a UQX, and the electron is coming in. When it enters the electric field, right? As we said, it's going to follow a parabolic path until it emerges, right? But what are we noticing? We're noticing that the displacement is coming down. It's coming down towards the positive plate, right? So wherever it started from, it's gonna end up lower and lower and lower and lower. So that's a negative displacement, right? So because the electron is coming down, down, down parabolically, this is how we had drawn it earlier. It's like a parabolic path, right? So because it's wherever it starts from, it's gradually coming down. That's a negative displacement from where it started or where it came in, right? So that's what this whole negative displacement thing is about. It's a negative vertical displacement. So it means that the displacement is going in this direction, right? All right. So that's what negative vertical displacement means, just so we're aware of that. It's coming down from where it started, okay? All right, going down towards the positive plate. So here we are now, we have the time. Here's our time. It's in second times 10 to the minus 9, so that's nanoseconds. And so here are the times there. And then we have to fill out the time squared, and that's going to be times 10 to the minus 18. We have to fill out that here, and then we have to fill out the negative vertical displacement SY. That's in meters times 10 to the minus 3. So that's technically just millimeters, right? So we have to fill out that table. That's what we're being asked to do. So we have to complete row 2 and row 3 in the table. So literally all we're going to do for the time is what? We're just going to square this, right? So if we square all of these times, this is what we're going to get. We're going to come out with these values when we just square those in our calculator. This one is going to be 0. This one is going to be 0.64. That's t squared, right? This one will be 2.56. This one will be 5.76. This one will be 10.24. And this one will be 16, right? Now the negative vertical displacement is SY. And earlier we said what SY was. We derived what it would be, right? And we had said that SY would be equal to half EQ over M times T, or in other words, it's half AT. So it's half AE times T, of course, squared, okay? T is squared. All right, so that's what we had. That's what we had from earlier. No, we just calculated AE. So essentially what we're gonna do is we're gonna do half of that AE, which was 7.32 times 10 to the 14 meters per second squared. We don't have to put the units in there, but that's an acceleration, and we're going to multiply that by the t squared value. Okay, So that's what we're gonna do in order to fill out this row. So to show you the very first one, well, the very first one is 0, right? Because the t squared is 0. So if I put 0 here, the whole thing will become 0. So I know that my first column would be 0. But for this one, I have to plug in 0.64 times 10 to the minus 18, okay? So that's what we have to plug in here. So if let me go ahead and do that. So it's gonna be half of 7.32 times 10 to the 14. And then the time we said is 0.64 times 10 to the negative 18. So that's my t squared value. I literally just took it from here, okay? Because that's t squared. And so I plug that in here, taking into account that it's raised to the 10 to the minus 18. And then I'll come up with a value there for this one of 0.23. Okay, so that's what I got there. 0.23 times 10 to the minus 3. So that's in millimeters here. So I'm just going to drop that here. Okay, 0.23. All right. So I'm gonna do it similar for all of these guys. Just plug in their t squared, plug in t squared, plug in t squared, plug in t squared until I fill up the whole table. And when I do that, this is what I end up with. 0.94 for that one, 2.1 for that one, and then 3.75 for that one, and then 5.86 for this one. Okay, remember these are all times 10 to the minus 3, so they're right. Make sure that you're aware of that these are times 10 to the minus 3. All right, so let's clear that now. We've completed row 2 and row 3. All right, so let us just clear the bottom piece and then keep the table for future reference, okay? So let's just clear all of this. All right, so let's go ahead now. So that was 1C, part 1. All right. So part 2 says we're supposed to plot a graph of negative vertical displacement. So this versus time. Okay. So this versus time is what we're plotting. Okay, and then we're going to have to draw a best smooth curve through the points. All right, so here's my plot now. Let me clear this. Here's my plot, right? So we're showing negative vertical displacement on the y, and then we're showing time up here. Remember, keep the units consistent. It's in second times 10 to the minus 9. This is in meters times 10 to the minus 3. So if we just plot the data from the table, that would be carried over. So this is what I got, right? Again, look at this. Follows a parabolic path. You see that? It follows a parabolic path. So that's what's going on inside of the electric field there. The electron is following that parabolic path. So we see that parabola right here. All right, so that's my graph. This is my time, and this is my negative displacement. The electron is falling down or being pulled downwards towards the positive plate. So that's exactly what the graph is showing here. Okay? All right, so that was what we needed to draw here. So let's move ahead. So it says that the electrons traverse the field in 3.75 nanoseconds, right? So from the time the electron jump into when it jump out, it's 3.75 nanoseconds. So let me just go back to this image and show you, right? So what we're saying is that when the electron comes in here, you see the time from it comes in here to when it emerges here, that time they're telling us that it takes 3.75 nanoseconds to do that, right? To completely clear the electric field. That's how long it takes, right? All right, so just keep that in mind. So it would have horizontally, it would have covered this distance here, right? 5 centimeters in that amount of time horizontally. All right, so let's go back to the question now. Right. So it traversed the field in that amount of time. So we're going to use the graph that we just drew to determine how far from the horizontal axis of the plates the beam will emerge as it exits the space between the plates. So here it is now, 3.75 nanoseconds. Let's find that time on our X so that it's right here, right? 3.75, we're going to come down and meet the curve and then find the corresponding negative vertical displacement, right? And it turns out that that negative vertical displacement that corresponds to that time of 3.75 nanoseconds is, so the S in the Y at 3.75 nanoseconds is equal to negative 5.19 times 10 to the minus 3 meters, right? So that's that. That's how far from the horizontal axis of the plates the beam will emerge. Okay, so that's our answer here. All right, so moving right along. All right, so now we're being asked to calculate the vertical velocity of the electron beam and hence its direction of travel on emerging from the plates, right? So whenever you see direction of travel, you know that they're asking us about an angle, right? So here's the picture again. We need to always go back to our picture, right? It helps us a lot in terms of just putting everything into perspective. All right, so again, the electron enters the electric field. It follows a parabolic path within until it comes out. It emerges out here, and it's following a straight line as it emerges. It's emerging with a velocity v. That velocity has a vertical component and a horizontal component, and we can show that by showing those components there. So in this direction, it would be the velocity, the vertical component. And then up here, of course, you know, that would have been the horizontal component of the velocity, right? So the first thing that we have to do, let's find Vy. Let's find the vertical velocity. That's what they asked us to do first of all. So we're going to go ahead and do that. We already know the formula for it from our table that we filled out earlier on, that the vertical velocity, right, for an electron that's passing through an electric field, we know it will be the acceleration times the time, right? And so Vy, then we know the acceleration from earlier is 7.3 times 10 to the 14. And then the time is the time that it took to emerge, right? So that's the Y component as it is emerging, it took 3.75 nanoseconds to come through. So that's the time that we're going to put in here. So that's 10 to the minus 9. And so our Vy then is going to be equal to 2.75 times 10 to the 6 meters per second, right? So that's our vertical velocity. So they asked us to find that. That's an answer. So we're just going to box that answer. Okay. So that's our vertical velocity of the electron beam. Okay. All right. So now let us go ahead and see what we would need to find the direction, right? To find the direction, we're going to have to do the tangent. So we're going to do the tan theta of the vertical velocity over the horizontal velocity, right? So that's our angle that the thing emerges at, that the electron emerges at. And so opposite is Vy, adjacent is Vx. We just found Vy, so we know what we need to put in here, but we need to find Vx, right? No, this Vx, that Vx, guys, is coming from the beginning, right? Initially, we had UQx, and because the electric field is only acting in the vertical direction, the horizontal velocity never changes, right? Whatever it was at the beginning is what it's going to be at the end because the electric field is not going to affect it, right? It's only going to affect the Y. And so your X velocity or your horizontal velocity at the beginning is going to be the exact same at the end, right? And so we can write that here and say that UQX which is your initial horizontal velocity, is going to be also your final horizontal velocity. So now what do we have to do? We have to find whatever UQX was, right? And to do that, we had an equation SX that we were given is equal to UQX times T, right? Initially, that's what we have. And so if I need to find UQX, I'm going to do SX over T is equal to UQX, right? All right. So let's find out now. What is SX? SX is the displacement in the X direction. This is our X direction. So the displacement is what? 5 centimeters. So I'm going to put SX there. So that's 5 centimeters. And the time that it took to traverse to come through the whole thing, again, was 3.75 nanometers. So I'm going to put that in the bottom for my time. Okay. And so when I do that, I work that through, I'm going to come out with a value for my initial horizontal velocity, aka my final horizontal velocity, because it's not changing. That will end up being 1.33 times 10 to the 7 meters per second, because it's a velocity, right? So that is it. And that's what I need to plug in here now to be able to find my theta eventually. Okay, so remember the key thing here, guys, is to realize that it is a horizontal velocity. So it's not being affected by the electric field because no force is being felt horizontally. All the force that the electron feels is going to be felt vertically. So only our Vy would have changed, okay? All right. So here it is now. We're going to just plug in this in here and we already have that. So I'm going to plug in 2.75 times 10 to the 6 divided by 1.33 times 10 to the 7th, right? So this is 10 to the 6th, if that wasn't clear. When I work that through, I'm going to come up with a value of 0.207, right? So that's what tan theta is equal to. So if I need to find theta, I'm going to do inverse tan of that number. So that would be tan inverse of 0.207, right? And so that theta will be equal to 11.7 degrees. So that is the direction of travel as the electron emerges from the plate. So that's that angle right there. It emerges at an angle of 11.7 degrees. Okay, so let's box that in. These are the two things that we need to put here to complete this question. Okay, so that's our vertical velocity and that's the direction of travel. And with that, we have come to the end of this question. So definitely give this video a like, subscribe to the channel, and if you look on your left here, you'll see the next video up. And if you look on the right, you'll see our Module 1 playlist, where you'll find tons more interesting content that will be helpful in getting you prepared for your exam. Okay? Thanks for watching, and we'll see you in our next video.